In my videos so far, I've only talked about supervised machine learning. Supervised means that the models are trained with a set of example inputs labeled with their correct outputs. And you can get pretty far just with supervised learning. In fact, generative models such as autoregression and diffusion are actually just supervised learning under the hood. But in this video, I want to talk about the technology behind the recent advances in reasoning LLMs. Reinforcement learning. You see, the problem with supervised learning is that it trains the model to reproduce the labels you give it. If you train a model on a bunch of code written by humans, it will learn to generate a similar style of code. But what if you want the model to write code better than a human would? What if you want the model to solve a problem that no human can? In order to achieve this, we need to go beyond supervised learning. We need an entirely new paradigm of machine learning, right? Well, actually no. It turns out reinforcement learning is also just supervised learning under the hood. Yes, all of machine learning really is just curve fitting. To see what I mean, let's consider an example reinforcement learning problem. Suppose we wanted to train a large language model to solve programming tasks. We have a dataset where each input is a textual description of a programming task, and we want the model to output a program which solves that task. But in order to get these solution programs to use as labels, we would need to solve all of these tasks ourselves. And that would be really expensive and time-consuming, and maybe there are some problems that we don't even know how to solve. So instead, we will train our model using a scoring function. The scoring function is a program which checks that the model's output compiles correctly and that it passes some random test cases. If the model's output program passes the tests, it gets a score of 1. Otherwise, it gets a score of -1. It's much easier to write these test programs compared to fully solving the tasks, so this scoring function is much cheaper to make compared to labels. We want to train the model to produce outputs which maximize the score function. This is now a reinforcement learning problem. And the only difference between this and our usual supervised learning is that we are using a score function to define the desired output instead of labels. So how do we train the model in this case? Well, usually when we train a model with labels, we just compute the gradient of the distance between the model's output and the label, with respect to the model weights. Which tells us if we make a small change to a weight, will that bring the model's output closer or further to the label? And we can use this to update the model's weights with gradient descent. So we should be able to do the same thing here. We just need to compute the gradient of this score function, and that will tell us how to update the model. Except that the score function isn't differentiable. The score function takes as input a piece of text made of discrete characters. You can't vary the value of a character slightly. And if you change one character into another, that can completely change the value of the score function. This is not ideal for neural net training. We need to be able to make lots of small, gradual changes to reach the training objective. Fortunately, there is a neat little trick from statistics that we can use to differentiate anything. All we need to do is have the model output a probability distribution over every possible output. And actually, most neural nets, and especially language models, already do this. It's just that usually for training, we only care about matching the most likely output with the label, or in our case, maximizing the score of the most likely output. But if we instead think about randomly sampling an output from this probability distribution, then our training objective would be to maximize the expected score. But here's the neat part. The expected score is differentiable, even if the score function isn't. You can vary the probabilities smoothly, and the expectation will vary smoothly in turn. So now we have a differentiable training objective, and all we need to do is compute its gradient. This gradient is equal to the sum over outputs of the score of that output times the gradient of the probability of that output. And, wait a minute, we have a problem here. In order to compute this gradient, we need to run the score function on every possible output. And for our programming task, an output is, well, a block of text. Supposing we have a maximum output size of 2,000 tokens and a standard vocabulary size of 50,000 tokens, the number of possible outputs is 50,000 to the power of 2,000. And yeah, we're not going to compute that. Fortunately, statisticians have already thought of a solution to this problem as well: random sampling. If you want to compute the expected value of a function under some probability distribution, you can draw a bunch of random samples from that distribution, evaluate the function on each sample, and average the result. This quantity, known as the sample mean, converges to the expected value as the number of samples used is increased. And often, the sample mean will be very close to the expected value with far fewer samples than the number of possible values. This is because the values with the largest probability usually contribute the most to the expected value. And when you randomly sample, you're more likely to get those values. So it's almost like sorting all the terms in the sum by their size and then adding them in that order. Obviously, this gets you closer to the total value of the sum faster compared to adding them in a random order. So going back to our gradient, we just need to rewrite it as an expectation over samples from the model's output distribution, which we can do by multiplying and dividing each term by the probability of y. This then becomes the expectation over the output distribution of the score times gradient of the probability divided by the probability. And we can approximate this expectation with random samples. To do this approximation, we randomly sample a bunch of outputs from the model, compute this expression for each output, and average the result. Assuming we have enough samples, this sample mean will approximate the gradient, so we can just plug it into any standard supervised learning framework to train our model. Oh, and by the way, this term here, the derivative of the probability of y divided by the probability of y, this is actually equal to the derivative of the log of the probability of y. This follows directly from the identity the derivative of log of x is equal to 1 over x. And usually you will see the equation presented in this form with the log, because it's considered simpler. The log version is also easier to implement in standard deep learning frameworks, which use automatic differentiation. In these frameworks, you have to specify a loss function which is automatically differentiated and minimized. You can simply compute the sample mean of score times log probability and use this as the loss function, which when differentiated becomes the quantity that we want to evaluate. This algorithm we've just developed is known as policy gradients. By the way, in reinforcement learning, we call the model's output probability distribution its policy, because saying output probability distribution all the time gets really annoying. And policy gradients is a perfectly good reinforcement learning algorithm. In fact, policy gradients was the main reinforcement learning algorithm used to train AlphaGo, which was the first computer program to beat the world's best human Go players. And it basically just amounts to do supervised learning with the gradient approximated by random samples. Now, while this basic version of policy gradients was widely used back in the day, there have been several improvements made to it since then. So if we want a truly modern state-of-the-art reinforcement learning algorithm, we need to do a bit more work. The main flaw with policy gradients is that one little caveat I mentioned earlier, assuming we have enough samples. That assumption is almost always false in practice. While the sampling approach needs far fewer samples than the number of possible outputs, it still usually needs more samples than you can afford to compute, so you end up with pretty poor gradient approximations. If we want our reinforcement learning algorithm to perform better, we need better ways of approximating this gradient using fewer samples. And in order to understand how to get more efficient approximations, we need to know a bit more statistics. As we saw before, when you evaluate a function on samples and average the result, you will converge to the expected value as the number of samples approaches infinity. But for finite sample sizes, there will be an error, and that error is expected to be equal to the variance divided by the number of samples. The variance, which is the expected distance between a sampled value and the expected value, measures on average how far a sampled value is from the expected value. The smaller the variance, the fewer samples you need to approximate the expected value. In the extreme case, when the variance is 0, you'll get the exact expected value after just one sample. But unfortunately for us, in practice, for the kinds of tasks we use reinforcement learning for, the variance of our gradient estimator is huge. So our goal is to find another function which has a smaller variance but the same expected value as our policy gradient approximation. If we can find that, then we can get better gradient approximations with the same number of samples. And one very simple way of doing this is to subtract a constant baseline value from the scores. If you subtract a constant value from the score of every output, that does not change the expected value at all. You can verify this with some quick algebra. But subtracting that baseline can change the variance. To see why, let's consider a simple example. We have three possible outputs. The first two have a score of 1, and the third has a score of 10. The model outputs unnormalized probabilities of 2, 1, and 1, which we then normalize by dividing by their sum. The gradient of the log probability of an output is a vector which is positive for that output and negative for the others. In this case, the best probability distribution that the model can output assigns a probability of 0 to the first two outputs and 1 to the third output. So the true gradient will push the model's policy in this direction, making the best output more likely and all others less likely. But if we try to approximate this gradient using a random sample, we find that if we sample one of the first two outputs, then our estimated gradient is positive for that output. This happens because even though the score is really low, it's still a positive number. This makes our estimated gradient quite different to the true gradient, so we have a large variance. If we first subtract 4 from every score, then no matter which output we sample, we get a gradient that pushes the sampled output's probability in the same direction as the true gradient. Hence the variance is lower, and we need fewer samples to approximate the gradient. So in general, we want to subtract the baseline value which minimizes the variance. But it's actually really hard to compute that value, so instead we just use the average score as the baseline, which works pretty well in practice. With the average score as the baseline, outputs which are better than average will have positive gradients, and those which are worse than average will have negative gradients, which is usually pretty close to the true gradient. There are a few different ways you can estimate the average score. The most straightforward way is to just sample a bunch of outputs and compute the mean of their scores. But the most common way is to train another neural network to predict the scores. Over time, this second neural network, called the value network, learns to predict what the average score for an input will be. Using a value network is usually preferred because it tends to give more accurate estimations, although it does have the downside that you need to train 2 models instead of 1. Also, note that I have just been talking about one training example, but each training example can have its own different baseline value, which is the average output score for that input. Some inputs might be really easy, and most of the model's outputs for that input will get a high score. For those inputs, the baseline would be higher, so that only outputs which are better than the model's average score for that input are made more likely. Alright, so by adding a baseline to policy gradients, we can reduce the variance and therefore get better gradient approximations. The other way that we can improve our approximation is to just use more samples. The problem with using more samples is, of course, that it takes more compute to generate the samples and run the score function on them. And you have to redo this sampling process for every single training example. It adds up quickly. But what if we reuse the samples to do multiple steps of gradient descent? For example, we draw 10 times as many samples and then train the network for 10 steps of gradient descent, reusing those same samples. This way, we spend the same overall compute generating samples, but we effectively get to use 10 times larger sample sizes, making our gradient approximations that much better. Sounds like a great idea, right? But there's one little problem. As soon as you take a gradient descent step and you change the model's weights, the formula we derived for approximating the gradient no longer works. You see, in our formula, we express the gradient as an expectation over samples from the model's policy. And remember, we are computing the gradient with respect to the model parameters, that is, the current model parameters. Once we update the model's parameters with gradient descent, at the next step, we need to evaluate the gradient at the new parameter values. That means we need to use samples from the policy generated by the new parameters. If we try to approximate this expectation using the old samples, it will not converge to the new gradient. But there is a simple fix. We just need to rewrite the gradient as an expectation over samples from the old distribution, which we can do by multiplying and dividing by the old probabilities. There. Now we can use samples from the old policy to estimate gradients for the new parameter values. This is also an old trick from statistics. It's known as importance sampling. It allows you to estimate an expected value over one distribution using samples from another distribution. And if this sounds too good to be true, that's because it is. Importance sampling comes at a cost. It can drastically change the variance of the estimation. Generally, the more different the two distributions are, the higher the variance of the importance sampling estimator will be. So, while you can use samples from another distribution, the more different it is from the one you're trying to estimate, the more samples you will need to use. And this is a problem for us, because when we update the model with multiple steps of gradient descent, it's possible for the new policy to become quite different to the old one, which means the variance of this estimator blows up and your gradient approximations become bad and the model fails to learn. So, if we are going to do multiple steps of gradient descent, we need to do something to ensure that the new probabilities don't stray too far away from the old ones. And the most popular way of doing this is with a method known as proximal policy optimization, or PPO for short. PPO aims to keep the ratio of new to old probabilities within 1 minus epsilon and 1 plus epsilon, where epsilon is a hyperparameter usually set to 0.2. Simply put, it doesn't allow the new probability to change more than 20% from its old value. One way to achieve this is to set the score to 0 once the probability ratio falls outside of the allowed range. This will prevent any further change to the new probability. But this has the limitation that once the new probability falls outside of the allowed range, it just stops learning completely. PPO does something slightly more clever. It sets the score to 0 only when the ratio is outside of the allowed range, and the current gradient would push it even further outside. The change to the new probability is determined by the score. If the score is positive, the probability will be increased. If the score is negative, the probability will be decreased. When the new probability is less than the old one, we want to allow any change that increases the new probability, because that brings it closer to the old value. Similarly, when the new probability is greater, we want to allow any change that decreases it. This logic can be summarized by checking if the sign of the score is the same as the sign of the difference between new and old probabilities. In summary, we only set the score to 0 when the probability ratio is outside of the allowed range, and the current gradient descent step would push it even further outside of the range. This can be implemented in deep learning frameworks as the following loss function. As an exercise, you can check that when you take its derivative, you get the objective I just described. And there we have it. This is the PPO algorithm, which is a state-of-the-art reinforcement learning algorithm. In fact, this is what DeepSeek used to train their R1 reasoning language model. DeepSeek R1 was trained on various coding and mathematical reasoning datasets using a score function to check correctness. And PPO was the reinforcement learning algorithm used. In their paper, they call it Group Relative Policy Optimization, GRPO for short, but that just means that they used random samples to approximate the baseline average score, instead of training a separate value network as is typically done. DeepSeek chose not to use a value network because they found the cost of training another large language model wasn't worth the benefit. Oh, and by the way, a lot of people who learn about PPO have the misconception that the reason why PPO works better than regular policy gradients is because of the clipping in the training objective. So to be clear, that is not true. The reason why PPO works better is because of something that does not show up anywhere in the equations. PPO is trained for multiple steps of gradient descent per sampling, whereas policy gradients is only trained for one step. Everything you see in the PPO equation is just stuff you have to do to prevent policy gradients from completely breaking down when you train for more than one step. Alright, we have now developed a state-of-the-art reinforcement learning algorithm, and we did it in a purely supervised learning setup. Just by adapting supervised learning to work with a non-differentiable loss function, we have performed reinforcement learning. But this isn't how reinforcement learning is usually presented. Usually, everyone presents reinforcement learning as an entirely new paradigm of learning, with agents taking actions in an environment and learning from self-experience. For example, you've probably heard that AlphaGo learned to play Go by playing games against itself. And that seems quite different to what we've done. Well, it turns out that the algorithm we developed for non-differentiable supervised learning can be repurposed for self-learning in arbitrary environments, with a few slight modifications. Taking the example of Go, we can actually think of the game of Go as a supervised learning problem where there is only one training example in the dataset, the starting board. The output is a sequence of moves defining a complete game of Go from start to finish. Just like with a language model, we can use a neural network to auto-regressively generate probability distributions over moves, one at a time. And note that it produces the moves for both players, alternating between black and white each turn. The scoring function is then 1 if the final board state is winning for white, or -1 if it's losing. And we now have a supervised learning problem with a non-differentiable score function, just like before, and so we can apply PPO. Except that currently the score function only checks if white wins, and since the model controls both players' moves, it can just produce a game where black makes really bad moves to throw the game. What we really want is for the model to play as well as possible, trying to win from both sides. And we can achieve this by simply multiplying the score by -1 when calculating gradients for moves made by black. This will make it so that the network learns to make moves which cause white to lose when playing from the black position. Now when we sample an output to estimate the gradient, the model is effectively playing a full game of Go against itself, and the gradient descent step will change the model to make slightly better moves from both sides. But there is one way in which Go is significantly different from a supervised learning problem. In Go, there is an opponent, and the opponent can do, well, anything, even things that are suboptimal. With our current setup, the network is just being trained to produce the optimal sequence of moves. In principle, the network should eventually converge to a policy which just assigns a probability of 1 to the optimal move and a probability of 0 to all others. Then the network would just generate the same sequence of optimal moves every time. And this would be exactly what you want if the opponent is also playing optimally. But if the opponent makes a suboptimal move, we can end up in a state that the network has never seen before during training. After all, it was only trained to play against its own optimal play. In such a never-before-seen position, the model is likely to make a bad move. So to prevent this, it's common to, during training, force the model to explore situations it wouldn't normally be in. One common way of doing this is to replace the neural net's chosen move with a completely random move every now and then. This ensures that the network gets some experience playing against all sorts of moves, even suboptimal ones. And that is all you need to do to make a superhuman Go-playing bot. This same setup will work for a whole bunch of different environments too, not just Go. In other environments, such as Atari arcade games, you get points periodically throughout play, and the goal is to maximize the sum of points obtained. We can also handle these environments by treating the entire sequence of actions as a single output and using the sum of points obtained as the score. Although, it turns out that if you instead only use the sum of remaining points as the score for each action, your gradient approximator will have lower variance. Intuitively, this is because an action can't affect the points you get before you took it, only those after taking it. So by removing dependency on points that came before the action, you are removing a source of variance. By the way, in reinforcement learning, we usually refer to these points as reward. Formally, an environment is given by a set of states, a set of actions the model can take, and a reward function which maps a state and an action to a reward. The model is a function which maps states to actions, and the goal is to maximize the sum of rewards. Our programming example, Go, the Atari games, and many other tasks can be expressed in this general framework of maximizing rewards in an environment. And our PPO algorithm can be used in any general environment. Well, almost any environment. There is still one type of environment that we can't handle. You see, all of the environments we've considered so far have one very important property. They end. In Go, the game ends after a few hundred moves, so you can just wait until the end of the game to see what the outcome was, and use that as the score to update the model. But what if you wanted to train a model in an environment that doesn't end? For example, what about living organisms? They too use reinforcement learning to tune their behaviors so they experience as much pleasure as possible over the course of their life. If you're a cat learning how to hunt, you can't wait until the end of your life before you learn anything. I mean, you could, but it wouldn't be a very long life. In order to be successful here, you need to learn in real time. You need to update your model every time you take an action and receive a reward. But how can we train the model to maximize the sum of future rewards before we even know what the future rewards will be? It turns out this is actually possible, and the key lies in the valuator network. Remember, one way of implementing the baseline is to train another valuator network to predict the average score for an input. Well, there is a way to train such a valuator in real time. The trick is to realize that the expected sum of future rewards obeys this equation. The score of the current action is equal to the reward we get from it plus the score of the next action. So rather than training the valuator network to output the sum of future rewards, we can instead train it to satisfy this relationship. Specifically, we evaluate the valuator network before and after taking an action, and train it so that the difference in its outputs is equal to the reward for that action. If the valuator network obeys this equation for all actions, then its outputs must be equal to the expected sums of future rewards. But when we train it like this, we can perform a gradient descent update immediately after every action. We don't need to wait until the end. This method of training is called temporal difference learning. And now that we have a valuator, we can use it to train the policy network too. The score that we want to use to train the policy is the sum of future rewards. This should be equal to the current reward plus the sum of future rewards, which is exactly what the valuator network is being trained to estimate. And now we can use this to train the policy network after every action as well. Using the valuator to estimate the future rewards also has another benefit, which is it reduces the variance of the gradient estimation. Intuitively, this way the gradient contribution only depends on the immediate reward and not everything after, so there is less variance. But there is a downside, which is that if the valuator network isn't accurate, and it often won't be, then this can introduce bias into the estimation. That is, the gradient you converge to won't be the correct gradient. So there's a trade-off. You can use the immediate reward for a lower variance but higher bias estimation, or you can wait until the end and use the sum of rewards for a higher variance but lower bias estimate. And in fact, you can do something in between, where you wait for, say, 10 actions, and then use the valuator to estimate the remaining sum of rewards after that. This will give a variance and bias somewhere in the middle. In practice, it is common to use a weighted average over multiple time horizons, which tends to give the best trade-off in variance to bias. This method is known as generalized advantage estimation, and it is pretty much always used in long horizon environments. One last thing. When you train the valuator network using temporal difference learning, it can cause some instability during training. To fix this, it is common to use an old version of the valuator network to generate values for the next action. Typically, you keep another copy of the valuator network, and after each training step, interpolate the copy network with the new weights, with a small interpolation value, usually 0.01. This way, the duplicate network weight values are a weighted combination of old networks, and this greatly stabilizes training. Alright, you now know everything you need to know in order to successfully apply reinforcement learning in absolutely any environment. But PPO is just one reinforcement learning algorithm. There are others, such as deep Q networks, soft actor critic, deep deterministic policy gradients, and many more. And in some environments, these other algorithms can perform even better than PPO. So if you really want to know everything there is to know about reinforcement learning, you'll want to hit that subscribe button so you don't miss my future videos about all of the other ways to do reinforcement learning.